Welcome to 2.4, Local Extrema and Optimization. This is our final learning section of our calculus unit. Let's get started. Our local extrema are our local maximum and minimum points. These are turning points in your function. A maximum occurs when you switch from a positive gradient to a negative gradient. And right there at the local maximum, your gradient is equal to 0. A minimum occurs when a negative gradient turns and becomes a positive gradient. And again there, where it makes a switch, your gradient is equal to 0, which is your local minimum. So your local maximum and local minimum points are known as stationary points or turning points. And at any turning point, the gradient function or derivative is equal to 0. So to find the turning points of a function, first you're going to find the gradient function or derivative. Then you'll set it equal to 0 and solve the equation to get the x-coordinate of the turning point. To find the y-coordinate of the turning point, substitute the x-coordinate back into the original equation and solve for y. All right, let's take a look at the coordinates of the turning points of the curve x cubed minus 9x squared plus 24x minus 20. So the first thing that we need to do is we need to find the gradient function. So that is y prime equals, and that has an n of 3. A is 1. 3 times 1 is 3. X to the n minus 1. 3 minus 1 is 2. Moving on to n is 2. A is negative 9. 2 times negative 9 is negative 18. And x to the 2 minus 1 is going to be x to the 1, or just x. 24 is a, x is 1, n is 1, because it's x to the 1. So n times a is 24, 1 times 24. X to the 1 minus 1 is x to the 0, which is 1. 1 times 24 is 24, so no change there. And then negative 20 is our constant, so that becomes 0, which we don't include. Now, what I need to do is set this equal to 0 and solve. All right. If 3x squared plus 18x plus 24 is equal to 0, the first thing I want to do is factor out any GCF. And I see that all of these are divisible by 3. So I'm going to factor out the 3, which leaves me with x squared minus 6x plus 8. And that is equal to 0. Now, there's a number of ways that you can solve this. You can solve by factoring. You can solve using the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a. I'm going to factor. I know that the factors of positive 8 that add up to negative 6 are negative 2 and negative 4. And so I know that 3 times x minus 2 times x minus 4 must then equal 0. And that is the factored form of our gradient function. Next, I'm going to set each equal to 0 and solve. So x minus 2 equals 0. Well, I've got to move the 2 to get x by itself. So x equals 2. And then x minus 4 equals 0. I need to move the 4. Therefore, x equals 4. Now, in order to find the y-coordinate, for each one, I will plug them into the original equation. So, for point 1, my x is 2. Now, I'm going to plug 2 in here to the original equation. So that is 2 cubed minus 9 times 2 squared plus 24 times 2 minus 20. And my y value there is 0. For my next one, I'm going to plug in 4 to my original equation. I'm going to do that over here. 4, and we'll plug it in. So 4 cubed minus 9 times 4 squared plus 24 times 4 minus 20. And I get negative 4. Okay, so these are my 2 turning points in the function. So the question now is, are they a local maximum or a local minimum? So in order to find out, I'm going to find y prime of 1 and y prime of 3. And what that's going to tell me is what the function is doing on either side of 2. So y prime of 1, I am going to plug 1 into the gradient function. So that'll be 3 times 1 squared minus 18 times 1 plus 24. That is positive. All right. Let's do y prime of 3. Again, we're plugging this into the gradient function. So that is 3 times 3 squared minus 18 times 3 plus 24. And I get negative 3. So here I am decreasing. So I'm switching from increasing to decreasing. This is a local maximum. All right. Well, now I know here I'm decreasing. Here's a turning point, but don't guess. Let's evaluate at y prime of 5. And I chose these numbers because 1 is an x value that comes before 2. So that tells me what the gradient function does before x is 2. I chose 3 because it's between 2 and 4. That tells me what the gradient function is doing between those two values. And then I chose x of 5 because that's an x value greater than x is 4, which is at that turning point. So let's now plug 5 into our gradient function. 3 times 5 squared minus 18 times 5 plus 24 is 9. So I'm increasing again. So here I go from decreasing to increasing. This is a local minima. All right, let's try some more problems. Let's find the coordinates of any turning points of the curve, y equals x over 2 plus 8 over x, and determine their nature. So are they a maximum or are they a minimum? All right, I'm going to rewrite y. All right, and so x over 2 becomes 1/2 x. And then 8 over x becomes 8x to the negative 1. All right, so y prime is going to equal 1 times 1/2 is 1/2, and then x to the 1 minus 1 is x to the 0, so this is just 1/2. Next, negative 1 times 8 is negative 8, and x to the negative 1 minus 1 is negative 2. Okay, so this now is equal to 0. That's going to find me turning points. All right, so I'm going to solve 1/2 minus 8 over x squared equals 0. All right, I'm going to add 8 over x squared to both sides. So now I have 1/2 equals 8 over x squared. I am now going to cross multiply. X squared times 1 is x squared, and 2 times 8 is 16. Now, to find x, I take the square root, and the square root of 16 is both positive and negative 4. So negative 4, comma 4. All right, let's find our points. At negative 4, I'm going to do negative 4. Remember, I'm plugging back into the original equation. So negative 4 divided by 2 plus 8 divided by negative 4. I get negative 4. So that is one turning point. Then I'm going to plug in 4. So 4 divided by 2 plus 8 divided by 4 is 4. These are my two turning points or stationary points. So now I'm going to pick x values that fall below here in the middle and up here to help me determine the nature of these points. All right, so I'm going to section this off. I need to pick an x value less than negative 4. I'm going to go with negative 5. So y prime of negative 5. And then I need one between negative 4 and 4 that is not 0 because x is on the bottom of a fraction here. So I'm going to go with y prime of negative 1. And then I need an x value that's greater than 4. And so I'm going to go with y prime of 6. Okay, so now we're going to plug these into our gradient function. So get my calculator, and I'm going to start with negative 5. So That's 1/2 minus 8 times -5 to the -2. And I get 9/50. And in reality, we don't even really need to write the number so much as we need to say, hey, this is positive. All right. For y prime of -1, again, I'm plugging into my gradient function. 1/2 minus 8 times -1 to the -2 is -15/2. So this is negative. So I'm going from positive to negative. So that point is a maximum. And then here, y prime of 6, 1/2 minus 8 times 6 to the -2, that is positive. So from this point to this point, I'm going from negative to positive. So this is a minimum. All right. Let's determine coordinates of turning points and determine their nature for 3 more problems. All right, here we go. Y prime equals 1 times 9 is 9, and x to the 1 minus 1 is x to the 0. 2 times -3 is -6, and x to the 2 minus 1 is just x to the 1, which is x, and then my constant goes away. Setting this equal to 0, 9 minus 6x equals 0. I am going to subtract 9 from both sides. So -6x equals 9, or -9, I should say. Divide both sides by -6. X equals 9/6, or 3/2. Okay, so I am now going to plug that into my original equation to find the y that goes with that x. So 3/2. I'm going to do 9 times 3/2 minus 3 times 3/2 squared plus 8. And I get 59/4. All right, so let's check and see. Is this a maximum or a minimum? I'm going to choose an x value to evaluate in y prime of 1, because that is less than 3/2. And then I will go with y prime of 2, because that is greater than 3/2. You do not have to use the same points that I do. Your answer, or the value of your answer, should remain the same as far as is it positive or negative. All right, let's evaluate. So here I have 9 minus 6 times 1, and that is positive. Okay, now I have 9 minus 6 times 2, and that is negative. So going from positive to negative, I have a maximum. All right. Here, I am going to distribute that x. So y is equal to 9x plus 3x squared minus x cubed. So then y prime is equal to 1 times 9, which is 9. X to the 1 minus 1 is x to the 0. 2 times 3 is 6. And x to the 2 minus 1 is just x to the 1, or x. And 3 times negative 1 is minus 3. X to the 3 minus 1 is x squared. All right. Now I'm going to set that equal to 0, and I'm going to move everything over to this side and have 0 over here. So everything is going to change sign. 3x squared minus 6x minus 9 equals 0. I have a GCF of 3, so I'm going to factor out that 3, which leaves me with x squared minus 2x minus 3 equals 0. Now, the factors of negative 3 that add up to negative 2 would be negative 3 and 1, because negative 3 times 1 is negative 3, but negative 3 plus 1 is negative 2. So my fully factored form here is 3x plus 1 and x minus 3. And that's equal to 0. I need to set each factor equal to 0. And so if x plus 1 equals 0, then x must equal negative 1. And if x minus 3 equals 0, then x must equal 3. Let's look for our points. Plugging in negative 1 to my equation here, my original equation, I have negative 1 times 9 plus 3 times negative 1 minus negative 1 squared. And I get negative 5. For my next point, I have 3 as my x value. So again, I'm plugging that into my original function. 3 times 9 plus 3 times 3 minus 3 squared. 27. Okay, so I'm going to pick some x values from here, less than my first point, between my 2 points, and then greater than my second point. So I'll do y prime of, we'll go negative 3, y prime of maybe 1, that's between negative 1 and 3, and then y prime of 5, which is greater than the x value of 3. Okay, I'm just looking, is it positive or is it negative? Okay, this, remember, gets plugged into the gradient function. So 9 plus 6 times negative 3 minus 3 times negative 3 squared. Let me try that one more time. I think I put an extra negative in. 9 plus 6 times negative 3 minus negative 3 squared times 3. All right. So that is negative. Let's go over here to 1. Same thing. 9 plus 6 times 1 minus 3 times 1 squared. That is positive. And then over here to 5. 9 plus 6 times 5 minus 3 times 5 squared. That is negative. So I'm going from negative to positive here. So this is a minimum. Because remember, negative to positive is decreasing to increasing. And then here I go from positive to negative or increasing to decreasing. So this is a max. Okay. Now, last one of these, I have y equals x plus 9 over x, rewriting as y equals x plus 9x to the negative 1 to make finding the derivative a little bit easier for me. So then y prime equals 1 times 1 is 1, and x to the 1 minus 1 is x to the 0, plus negative 1 times 9 is negative 9, and x to the negative 1 minus 1 is x to the negative 2. Okay, setting this equal to 0, 1 minus, back to fraction form, 9 over x squared equals 0. Subtracting 9 over x squared from both sides, 1 equals 9 over x squared. If I multiply both sides by x squared to get rid of my denominator, I find that x squared equals 9. So, taking the square root, I find that x is equal to positive and negative 3, because remember, negative 3 times negative 3 also equals 9. So to set up my points, I have negative 3. I'll plug that in here. Negative 3 in my original equation plus 9 divided by negative 3 is negative 6. That is my y value here. And then positive 3, I've got 3 plus 9 divided by 3, which is positive 6. Now let's figure out their nature. Do a little separation here. I'm going to use a value of x that is less than negative 3. So I'll do y prime of negative 4. Remember that I cannot use 0 because I have x on the bottom of a fraction. So my second point will be y prime, let's go with 2. And then last, greater than 3, I'll go with y prime of 5. Remember, we're just looking. Is it positive or is it negative? We're plugging into our gradient function. So 1 minus 9 times -4 to the -2. I get a positive result. Next, 1 minus 9 times 2 to the -2. I get a negative result. And then finally, 1 minus 9 times 5 to the -2, I get a positive result. So going from a positive or increasing to decreasing, this is a max. And then going from decreasing to increasing, this is a min. All right, good job. Now let's look at some optimization problems. First, we need to figure out how do we set up an optimization problem. So when we're optimizing, we're finding the best possible solution. So suppose you wanted to maximize the area of a rectangular field that borders a straight canal and is enclosed on 3 sides by 120 meters of fencing. In this case, we would need a model for the area of the field for different lengths and widths. So the first thing we want to do is identify our variables. And our variables are the width of the field, the length of the field, and the area of the field. Next, we need to identify any constraints on the problem. And in this case, our constraint is that we only have 120 meters of fencing. So if we kind of think about it in a way that your width is your X and your length is your Y, then if the canal borders the length, we would have 1 Y plus 2 X's, or the 2 widths, and that would have to be less than or equal to 120. Actually, no, they said it is 120. So we're going to say equal to 120. That is our constraint. Now, it often helps to try a few numerical examples in order to put the problem in context and indicate the method. So if the width is 20, then let's see, 2 times 20 is 40, and 120, let me make a little punctuation there, 120 minus 40 is 80. So if your width is 20, then your length is 80, and so your area then would be 20 times 80. 20 times 80 is 1,600 square meters. All right. Well, what's something else we could do? Maybe say the width is 50. Then 2 times 50 is 100. So, okay, what's that leave for length then? 120 minus 100 equals 20. So there your length is 20. So your area would be 50 for the width times 20 for the length, and 50 times 20 is 1,000 square meters. Well, you can already see that with scenario 1, I got a bigger field fenced in. So now we're going to set up our model by defining our variables, writing our constraint algebraically, and then using the formula for the constraint to write the area function using just one variable. All right. We've already kind of talked about, we decided that let x equal the width, let y equal the length, and let capital A equal the area. We wrote our constraint algebraically up here when we were kind of talking it out, where y plus 2x, or 1 length plus 2 width, equals the 120 meters of fencing that I'm working with. Okay, so let's use the formula for the constraint to write the area function using just one variable. So I know that area equals length times width, yx. I also know that here I can subtract that 2x to get y equals negative 2x plus 120. Area then equals y, which is negative 2x plus 120 times x. So what I did here is I substituted the what is equal to the y in for the y. All right. From here, we are going to model the area of the field. And we model it as a function. And I'm going to draw this so we don't get these ridiculous red lines. That area as a function of x is equal to negative 2x plus 120 times x. Or we could write it as negative 2x squared plus 120 x. And I simply got that from distributing that x across the function. Now, finally, to find the maximum area or the optimal solution, we're going to set the gradient function equal to 0. So I need to find a prime. All right. 2 times negative 2 is negative 4. And x to the 2 minus 1 is just x to the 1, or x. And then 1 times 120 is 120. X to the 1 minus 1 is x to the 0, so that doesn't go anywhere. Alrighty, and so we find here negative 4x plus 120 is our gradient function. Now we're going to set that equal to 0. And I am going to subtract 120 from both sides. So negative 4x equals negative 120. Divide both sides then by negative 4, and x equals 30. All right, so in order to maximize area, my width must be 30. To find then the maximum area, I am going to plug in x to my area function here. All right, so a of 30 equals, so I'm going to start here with negative 2 times 30 squared plus 120 times 30. And I find that I get an answer of 1,800, which you'll note is larger than either of the ones we found earlier, which makes sense. It's our maximum area. So our maximum area is 1,800. I believe this was meters. Yes, it was meters. So 1,800 square meters. So in optimization problems, we use differentiation to find an optimal value, either the max or the min of a function as two variables interact with each other. Let's look at some examples. Here we're going to optimize the function a equals 3xy subject to the constraint x plus y equals 20, and then we'll determine, is that value a max or a min? Okay, so the first thing I need to look at is, what are my variables? My variables are a, x, and y. I also know that my constraint is that x plus y must equal 20. That's it written algebraically. Now, what I can do is I can rework my constraint to solve for y. And I do that by moving x to the other side. Y equals, I'll move x by subtracting it. Negative x plus 20. Now, I know that area, or A, equals 3xy. So what I'm going to do is I'm going to plug in my reworked constraint in place of y. So now A is 3x negative x plus 20. So now I've rewritten A in terms of x. And so now I have, if I kind of just take everything together, I have a function a of x that equals, so I'm going to distribute my 3x to my negative x and get negative 3x squared. And then I'll distribute my 3x to my 20. 3 times 20 is 60, times x is 60x. So there is my function rewritten in terms of x. Now let's find a prime. Two times negative 3 is negative 6. x to the 2 minus 1 is x to the 1, or just x, plus 1 times 60 is 60, and x to the 1 minus 1 is x to the 0, which goes away. All right, I now need to set this equal to 0. And I'm going to subtract 60 from both sides to cancel it out on the left. So negative 6x equals negative 60. Divide both sides by negative 6, and we get x equals 10. All right. We are now going to plug that back in to our original. Actually, first we need to solve for y. And we will come right over here and plug that in to do so. So a of 10 equals negative 3 times 10 squared plus 60 times 10 is 300. So is this a maximum or is this a minimum? Well, what we'll do is we'll write our point of 10, 300, and we will check x values below it and above it in the gradient function. All right, I'm going to go with a prime of 5. And then I'm going to go with a prime of 13. So remember, because we're doing the prime, we're plugging into the gradient function here. All right, so that's negative 6 times 5 plus 60. That is positive. So there we're increasing. And then negative 6 times 13 plus 60, that is negative. So here we're decreasing. So it's a change from increasing to decreasing. This is a maximum. All right, one more example problem. Then I think you've got this. All right, find the minimum surface area of a cylinder which has a volume of 330 centimeters cubed. All right, I want the minimum volume. And I do have a constraint here. But first, let's see. I need my variables. My variables are V is my volume, SA is my surface area, R is my radius, and H is the height of that cylinder. Let's talk constraint. My constraint here is that my volume must be 330 cubic centimeters. So I'm going to write PI for pi. R squared H must equal 330. So I need to figure out a way to rewrite that constraint. So do I want to do this in terms of R or in terms of H? I'm going to go in terms of R. So I'm going to rewrite this as H equals, and H equals 330 divided by pi r squared. Okay, so now that I have that constraint down, I am going to rewrite my surface area in terms of r. So surface area now equals 2 pi r squared plus 2 pi r times, instead of h, we substitute in 330 over pi r squared. That is surface area in terms of the radius. So we can try and simplify down a little bit and say that SA of R is equal to 2 pi r squared plus 2 times 330 is 660. Pi divided by pi crosses out, and r divided by r squared leaves us with just r on bottom. There we go. Let's differentiate. So SA prime equals 2 times 2 pi is 4 pi. R to the 2 minus 1 is 1. Now, remember that 660 over R is equal to 660 R to the negative 1. So negative 1 times 660 is negative 660. And that is R to the negative 1 minus 1. That is R to the negative 2. That right there is my gradient function, and now I need to set it equal to 0. 4 pi r. Now, I can set it equal to 0 here, which immediately lets me know that I need to add 660 r negative 2 or 660 over r squared to both sides. So I'm just going to do that here. So 660 over r squared. Okay, now let's talk about what comes next. I'm going to multiply both sides by r squared, and we get 4 pi r cubed equals 660. I'm now going to divide both sides by 4 pi. So r cubed equals 660 over 4 pi. Now I have to take the cube root of both sides. And it's at this point that we're going to kind of forgo what I said about not using decimals. We're using decimals. We're going to round it 3 sig figs. So I'm going to take the cube root of 660 divided by 4 pi. And to 3 sig figs, my r is going to equal 3.74. Okay, got that. Now I need to plug that in to my function here to find the surface area. So the surface area then is going to be 2 pi times 3.74 squared plus 660 divided by r 3.74. And I get a surface area, of to 3 sig figs 264. Now let's not forget our units. For r, that's 1 measurement, so that is centimeters. For area, we've got 2 measurements multiplied by each other, so that is centimeters squared. So, is this no, actually that's it. We're good. Hey, let's not add more work than we have to. Excellent. All right. So, at this point, you can stop and do the practice problems on your own, or you can continue on and we can look at them together. Okay, let's start the practice. The first thing that we're asked to do is to show that h equals 100 over pi r squared. Well, I know that volume equals pi r squared h. I also know that here my tank must hold 100 cubic meters of water. So that is pi r squared times h equals 100. All right, then to get h by itself, I simply divide both sides by pi r squared. So h is equal to 100 over pi r squared. Now, this is for a manufacturing company designing a cylindrical tank for a local farm. That constraint tells us the tank must have a volume of 100 cubic meters of water. We want to minimize the amount of material used to manufacture the water tank. So we need to show that the surface area is represented by this equation. We can do that because we know that surface area equals 2 pi r squared plus 2 pi r h. However, we know that h is 100 over pi r squared, so we're going to substitute that in. 2 pi r squared plus 2 pi r, and instead of h, we're going to write 100 over pi r squared. Last but not least, we'll simplify. The 2 pi r squared stays the same. And then 2 times 100 is 200. The pi's cross out, and r divided by r squared is 1 over r, so r goes on the bottom, and there we've shown that surface area is 2 pi r squared plus 200 over r. Now let's find the derivative. Really quick, remember that this is 200 r to the negative 1. So to find s prime, 2 times 2 pi is 4 pi. And then we have r. 2 minus 1 is 1, so it's just 4 pi r. And then remember that is written 200 r to the negative 1. So negative 1 times 200 is negative 200 r. And then negative 1 minus 1 is negative 2. So now find the value of r that minimizes the surface area. Let's set it equal to 0 and solve. 4 pi r minus 200 over r squared equals 0. All right, so now I'm going to add 200 over r squared to both sides. So that's 4 pi r equals 200 over r squared. Next, we're going to multiply both sides by r squared. That will come up here. So 4 pi r cubed, because r times r squared is r cubed, equals 200. I'm now going to divide both sides by 4 pi. So r cubed equals 200 divided by 4 is 50. over pi. I was going to write pi to the -1, but no, just 50 over pi. All right. From here, I need to take the cube root of both sides. R equals, and I'm going to use my calculator and go to 3 sig figs. So the cube root of 50 divided by pi is 2.52. So my radius is 2.52, and that is in meters. Okay. Now, let's calculate the minimum surface area of the water tank. And if you want to make sure that you have a minimum, you can always take an X value or an R value that's less than this. Let's say 1. If I were to plug 1 in here and say 4 pi times 1 minus 200 times 1 to the -2, I would get a negative value. All right, negative. And then if I did something bigger, say 3, 4 pi times 3 minus 200 times 3 to the -2, I would get a positive value, which lets you know that I was descending and then ascending, or decreasing and then increasing. So yes, this is a minimum. You can always check that. All right, let's calculate the minimum surface area of the water tank without me drawing random lines on my paper. Okay, so then I'm going to plug in R to my function here. So S of 2.52 equals. And remember, from right up here, that is 2 pi, R is 2.52 squared, plus 200 divided by R, which is 2.52, and we find 3 sig figs that our minimum surface area is 119 meters squared. All right, guys, good job. I will see you next time for our third and final unit in math studies. Have a good one.